styles. And each style is a little bit different than the others. And it's dependent upon what the wording was and how you go about setting it up. Now, I think the first couple that we had, let's see, number 98. Number 98 was basically a straight factor problem. Did you have to factor it? No. But if you look at it, they're talking about the environment, group, responsibility, ecology, gardening, blah, 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 blah. They're saying that you have the area of the garden has to equal 800 square something. And they're giving you the two dimensions. They're giving you the dimensions of the rectangle being 60 minus x and x. I find the area of a rectangle. Times with, yeah. So you get x times 60 minus x, and it has to equal 800. Okay? Distribute out, you get 60x minus x squared is 800. And then when we have to factor something, we have to set aside equal 0. Whenever you factor something, you always want to make sure that you have your first term positive. You don't want to factor the first term a value is negative, because that's just awful. So we're going to get x squared minus 60x plus 800 is 0. Now, at first glance, you might be thinking, holy crap, I don't want to try to multiply what times what's 800 to get to 60 until you realize it's just 40 and 20. Okay. What's up? 98, the first one. So if you factor this, you get x minus 40, x minus 6, or excuse me, x minus 20, which means your zeros are at 40 and 20. Now, that gives you your values of x that are possible. Now, watch what happens. If I go back in here, if I use 40 for x, I get 20 for one side and 40 for the other. And if I use 20 for x, I get 20 for x and 40 for the other. Convenient, isn't it? Yeah. So those are your dimensions to your sides. Yeah.
Okay. Well, I got that right, but when I was doing it, it took an hour because I was trying to figure out how the 120 thing. What if the number doesn't? What if the number? Yeah, that was your thing.
It's there to distract you.
Well, how do you know that it's
We can't mess with you. Seriously, don't worry about it. Are you threatening me? I think she just threatened me, didn't she? Wow. Yeah. All right. Next one. Was electronics, right? Okay. Electronics. When you're dealing with the electronics, you're talking about the sales figure. That was very similar to, I think, the second one we did yesterday in the notes, when you had the shoe selling. It follows that pattern exactly. So you're selling home electronics, digital cameras, current price is $680. You sell about 70 of them each month. So when you're dealing with sales figures like this, you've got like your price, and then you've got sales, like sale amount, or how many. So when they start talking about increase in price or a decrease in price, you get increase in sale, that means that you have this set up like this every time. So what was your initial price you were selling the digital camera at? $680. At $680, how many of them per month were you selling? 70. So what I do here is I put those two together, because if I FOILed this out, 70 times the 680 would give me my total monthly revenue for that camera. Now, when it gets into the idea of increasing sales versus decreasing in prices, or vice versa, I think this one said that for each $20 decrease in price, 5 more cameras would be sold. So if I decrease the price once, what's my new sales price? 660, and how many would I sell? 75. If I decrease the price 4 times, I would be selling it for 600, and then I would increase my sales to 90. that this value here is this multiplier for the number of times is what's going to happen. How many times are you decreasing versus increasing your sales figure? So what happens is for every decrease in $20, decrease it once, decrease it twice, that X value is constant to the other one. And what we're trying to do here is find the zeros. Now, when we have this style, I'm always going to suggest that you use it in terms of intercept form because it's written in intercept form. Okay? So what we do is we find the zeros in each of our terms. Remember, terms generate zeros. So I have zeros here. If I set each of these equal to 0, 680 minus 20x is 0. Add it, and what do you get, 34 for that one? So we have a 0 at 34, and the other one is, I think, negative 14. Very good. So you have two zeros, negative 14 and 34. So graphically, remember what this looks like. I have negative 14 here, and I have 34 here. Those two values are on the same y line, which means they have to be equidistant to the axis of symmetry. That axis of symmetry gives you a vertex. That vertex here, since this winds up being down like a frown, gives you your maximum. That's where all this vocabulary comes in that I've been talking about all along about maximums, minimums, axis of symmetries, and things. Yes, sir? If you FOILed this out, your x squared term would be negative. Yep. Okay. So now, what's negative 14 plus 34? And what's after that? Gives you your axis of symmetry at 10. That means my x-coordinate for the vertex, where my maximum is located, is x, which means I should decrease this price 10 times. If I decrease this price 10 times, I will increase the sales 10 times. So if I decrease my price 10 times, I get 680, subtract 200. So if I sell my cameras for $480, I will then sell what's 70 plus 50. I will sell 120 cameras at $480, which generates the revenue, I think it was like 15 something. Question? I was close. 57,600. So that tells me my maximum revenue when I FOIL all that out is at that. Yes, sir. A midpoint. Yep, it's just the axis of symmetry of the zeros. That's how we get that x coordinate. And then we substitute in to figure out what the y is. Yes, sir. I substitute in 10 for x. The axis of symmetry. Okay? And that's where this comes from. If you decrease the price to $480, you will maximize your sales figures. You will sell 120 of them for an overall sales of 57,600. That's where that comes from. Okay? Dan, you're about to say something. I put 10 in for x. What's 5 times 10? And I add 70 to it. Okay? That's where this goes from. All right? The next one was the Big Bertha cannon, right? All right. So if you're doing the Big Bertha cannon, you have this equation, y equals negative 0.0196x squared plus 1.37x, where x is the horizontal distance traveled in miles. Where does a cannon start? At 0. The height of the cannon is at 0. Basically, that means it's shooting from ground level. Okay. You really get down to thinking about it. You've got a cannon. There's a little light for the fire. I'm drawing a cannon. And it shoots cannon. It looks pretty good. And it shoots cannonballs. Nice. That's pretty sweet. So think about what this means. The cannon itself is starting at some spot. It shoots a horizontal distance. The cannonball goes some vertical distance. But what's happening, since there's no C value here, it's starting from ground level. Whereas yesterday, when we had the shot put with the great awesome sound effect, it was starting at 5.5 feet up because she was holding it 5.5 feet up before she threw it. This one, the cannonball starts at the ground. Suspends in midair for a couple of minutes, and then it lands and goes kablamo, and it bounces and everybody dies. But anyway, so here's where knowing how to use the calculator comes into play. So this one, you have to use the calculator. So in your calculator, go to your y equals. Sorry, I just redoing my window. Okay. Go to your y equals, and we're going to put in the equation here. Let me back out these real quick. And we have negative 0.0196 x squared plus 1.37 x. And we have to throw it in there, and then we have to learn how to adjust windows. Okay. If I graph this, I put mine up as a 10 by 10 graph because I don't know where yours are sitting at right now. What we want is trying to figure out where is this going. What's the only quadrant we should be looking at? Quadrant 1. It starts at 0. It's going to go up and hit something. Okay? Yeah. How do I do what? I didn't hit zoom out. What did you hit? I'm not even doing any of that right now. I haven't shown you how to mess with windows yet. So I want to mess with the window to be just quadrant 1. So I go to the window. I don't keep my x max, or my x minimum. I'm going to leave it at, I'm going to put it to 0. Now this is in miles. So we have to take a guess of how many miles a cannon shoots. I don't know off the top of my head. I'm just going to put 50. 80,000, yeah. Obviously, my y minimum, I don't care what's happening below because it's going to go up and down. It's going to start at 0. It's going to end at 0. So I'm going to leave it at 0. And I don't know how high up in the air the cannonball goes. I'm going to say maybe 25. I'm just making stuff up. Okay. And now I hit graph again. And I'm just seeing if we get close. Ooh, I'm tall enough, but I'm not far enough out. See what I'm talking about here? So I'm just gonna do an x maximum of 100 then, or 75, whatever. It doesn't matter. You guys keep yelling that. So I do 75. What goes up must come down. You play around with the window to adjust to see what you're looking at. That's what takes time to get used to. Okay, that's what takes time to get used to. Yes, ma'am. What's that? Your window range is wrong. That means you have your minimum is bigger than your maximum. You put your x minimum at 75, or your x maximum at 50. That just means it's not. You were having a graph. You're using a minus sign, not a negative sign. And use the negative sign, guys, not the minus sign. So what we need to do here is it's asking us how far out did it shoot, which means I have to calculate the 0. So you hit second, calculate, option number 2. What the calculator is going to do now, it's going to search for boundaries. You're going to program the calculator to search for a left boundary and a right boundary. Basically, you're moving your cursor. This is something we're going to do a lot of here. We need to figure out what this value is, so we have to look at the left boundary and the right boundary. We're going to look at the value. It'll start calculating numbers in between that domain to figure out where it equals 0. So you move your cursor. Yours is a lot faster than this one. I don't know. It takes forever. No, it doesn't work. Not for the emulator. So I'm going to get it close to where it crosses over. And if you hit it one more time, you'll see how it gets, mine goes to negative. So I want to be to the left of where it goes negative and to the right of when it is negative. So I just move it back 1. I'm still positive my y value here. So I hit enter. I go to the other side where it goes below and it goes negative. Somewhere that means it had to equal 0. And I hit enter. Yes, who cares? Hit enter again. And there's my 0. My 0 occurs at 69.9 miles out. Okay. Obviously, depending on how your zoom was set or how your windows were set and where you did your left and right hand parameters, you may or may not be within a couple of tenths, a couple of hundredths, and that's okay. It's close enough because I know that there's a specific range that you can set things through. Okay. So if you think about it, can I just, for all intents and purposes, can I say that's roughly 70 miles? If you shot a cannon from here 70 miles that way, what are you going to hit? No, you actually go past Chicago. You land in Lake Michigan. You'll land. You go past Navy Pier, and you land in Lake Michigan if you shoot a cannon from here. Yeah. If you shot this cannon from the pier, it would land in Lake Michigan. So that's how far out it goes. Yes, sir. Oh, I thought you had like holding that you wanted to ask something. Okay. Now, again, it also asks you for what was the maximum height. So that's how we found our 0 to find the maximum height. You would do the same idea. Second, calculate and choose your option 4. And you do your left-hand boundary and right-hand boundary. But if we're using a rounding idea here, if I start at 0 and I end at 70, what happens in the middle? Axis of symmetry, which is at what? What is for argument's sake? If this is 0 and this is 70, where's that at? Like, yeah. Ish. If I throw 35 into the equation, that give me my maximum height then? It's close-ish. Or if you hit the calculator on the calculator, it'll find it for you as well. Okay? And we're just, obviously with this one, it's close enough to 70, you can kind of get away with that. That's okay. The horizontal distance of shot. It found to be calculated at 0. You knew it started at 0 and it ends at a 0. We're trying to figure out where did it cross the axis. By pressing buttons in the calculator, we rounded it up to 69.89, basically 7. We're just saying 70 because we can use a clean number. Yeah. I think it asks in the question, what was the maximum height of the cannonball? And to get the maximum height, you can do one of 2 things. Since this is pretty darn close to just saying 70, you can say that the axis of symmetry has to be at when x is 35. Well, if the axis of symmetry is at 35, that means that your x value for your maximum is 35. Substitute your y value. That's calculate maximum. Left boundary, right boundary. Just like you did with the 0. If you did it with the calculator again, second, calculate 4 is your maximum. You just got to move your cursor back to the left of where it looks like it was the peak. Go to the right of it, 34.95, so roughly 35, and then that means the maximum was at 23.94 miles. So that's where it is. Okay. I would just round, make it quicker, just to go through everything about 35. Okay. Next one was the quilt problem that mirrored the exact same thing we did for our first example yesterday. Quilting problem, you had a quilt that was, what, 4x2, I think? No, 4x5. And then you had a uniform of border of uniform width. Those were all those values of x going around. Turns into an area of shaded region problem. Your overall problem here becomes 4 plus 2x, 5 plus 2x. To get the area of a rectangle, you just multiply those two together. Then you have to subtract the inside where the picture is. So like I said, this is basically the exact same thing as the first example. 4 plus 2x times 5 plus 2x. Subtract out the area of the picture and set it equal to 10, because that's how much material you had to make the border. Okay? You're dealing with all areas. Foil it out, you get 20. 8x, 10x, you get 18x plus 4x squared minus 10 is 0. Set it aside equal to 0. 4x squared plus 18x plus 10 is 0. You're back to a factoring problem. You can do GCF right off the bat if you want, but you'll notice it's 40 to get you 18. So that's, oh. It's supposed to be, yeah, it should be negative 30. Yep, I was wondering why I screwed that up, because this should be negative 10 then. Yeah, this should have been minus 30. Sorry about that. I got a little ahead of myself. So you get, what times what's negative 40 to get add together to get positive 18. So that was 20 and 20 and negative 2, so it's not terrible to factor that one. So 4x squared minus 2x, 20x minus 10. And then take out the 10. Are the two things in the parentheses the same thing? That's a good sign. And the other one's 2x plus 10. That gives you zeros at 1/2 and negative 10, negative 5. That's perfect. You're done. Thanks. So you get 1/2 or negative 5. Which one of those makes sense for a border? Yeah, you go over a Hobby Lobby.
Yes, I like a negative half border around my poster, please.
I'm not a fan of a lot of their things, but sometimes they're cheap. Their ethics are sketchy. We'll leave it at that. Without getting too political in a math class, their ethics are real sketchy. Next page you did what? The airplane one, I think, was the next one? Does that sound right? Okay. So airplane. The length of a runway in feet needed for a small airplane to land is given by blah, where s is the airplane's speed in feet per second. The pilot is landing a small airplane on a runway 2,000 feet long. What's the maximum speed at which the pilot can land? So you've got the length of a runway modeled by 0.1. I'm going to use x because I can't handle s's. Minus 3x plus 22, where x is the runway length. No, sorry, x is the speed. Sorry. L is the runway. Okay. So if the pilot's landing on a runway that's 2,000 feet long, how fast can they be going? Okay. So you know that the runway has to equal 2,000. You get that, right? Okay. Set aside equal to 0. We can throw it in the calculator. That's one way to do it. We throw this into a calculator, we get 0 equals 0.1x squared minus 3x minus 1978, I believe. And now we're just trying to figure out what's the maximum speed that it can hit. So we're looking to where this equals 0 when x is positive. That's what this means. That's what you're trying to find here. You're looking at the parabola itself. Is it up like a cup because that first term is positive? So we're trying to figure out where does it cross the x-axis that gives you an x value that's positive, because it could be crossing on both sides. We know that it crosses the y-axis at negative 1978. So I don't carry anything going the other way, but I need to look for this one. This is another weird one with the window. Okay? So let's throw that in. Button. Clear it. Oh, it wasn't negative. Sorry, it was just 0.1 x squared. Was it minus 3? Minus 3x, then minus 1978. Yeah. We graph this. We don't know where it's going to cross. We got to kind of start taking a guess. Our last one had a window set that was a little bit weird. We obviously don't care about our x values being negative, so I can keep those being negative. But I need to figure out some x value that's positive. And I think right now we're stopped at 75, aren't we? Okay. So let's do this. Let's go to our window and guess that the airplane might be traveling hopefully 200. That's feet per second. That's pretty fast, isn't it? That's really fast. Okay, so, and then we'll do a y minimum just so we can see something down below there, which is maybe negative 100. So we know it's moving upward. We can get start to see where it's curving up to. And just try it. Oh, crossed. I'm just looking to where it crosses that it's positive. We don't want a negative speed. Does that make sense? I'm just guessing where I can try and find it. I put my y max at like 20, just so that way I had a little bit of room above it to see that it crossed. That's all. I think my y max is at 20. My y minimum is what, negative 100 maybe. And then now we do the same thing, but remember this curve is moving. It's moving upward. So if we're crossing the x-axis, our left boundary is going to be a negative number. Our right boundary would be a positive number. Yes, sir. Yeah, it's getting dead. I got more in the office. I'll get them later. That's okay. Hit your calculate. We're looking for a 0. Left boundary, I'm way below here, so I'm going to start moving until I start seeing my cursor. Yeah, sometimes if the curve is really has a real fast slope, it might move up real quick. So you just gotta. Oh, there it is. All right. So I'll have my left boundary, hit enter. Right boundary, hit enter, enter. 156.44 feet per second. That's pretty fast. What's your answer? Did you type in the correct equation? 0.1x squared minus 3x minus 1978. What's that? Oh, yeah, and that's why you'll be off by that. And if you're off by a couple hundredths or a tenth or two, that's not really all that bad, but 6? You done goofed. All right. Again, it's calculator trying to figure out what values mean. What values mean. I know that I think I said do the firefighter one next, but since I'm reading the telecommunication ones, so there's another way of solving some of these types of problems. And in order to solve some of these problems, we can actually go to our table to look for data. So in the telephone problem, back in my day, for the years of '89 to '96, that's my my wheelhouse. The amount of money, millions of dollars, was spent on long distance phone calls. So you may or may not be aware of this, but there were these things in people's homes called phones. They were called landlines. They actually had a cord. You could barely walk around the house with them until they came up with these things called portable phones that had these giant antennas and things you'd walk around with. Yes, sir. Oh yeah. Now, yeah. Nice. I saw one of those in Georgia 2 summers ago. It was pretty awesome. But also, back then, you had a local phone company and a long distance phone company. They weren't the same company. So you could buy local, I'm trying to tell you the history. You should be sorry. So your local phone company was like Illinois Bell. Your long distance company could have been like AT&T or Sprint, because they would take those lines and go further away with them. So you had 2 different phone bills you were always paying. It's really weird. But then all of a sudden this thing called a cell phone came out, and then, as they say, the rest is history. But in this one here, they're talking about the what was it, 0.56 something, this, and this, where 51, where t is time. So we have this formula for money. The amount spent was 0.56 t squared plus 0.488 t plus 51, where t is billions. Okay? So they're talking about this started in year 1989. So that means at year 0 is what year? 1989. In 1989, how much money was spent on long distance phone calls? Billions. How many billions? Louder? 51 billion. Because at year 0, when time is 0, that's your year 1989. So at year 0, you spent $51 billion on long distance phone calls. Okay? Now, here's what happens. Take your calculator out, put that in your y equals. 0.56x squared plus 0.488x plus 51. And now I don't care about the graph, because it's asked, if you read the question, it's asking us approximately what year were sales, 60 billion? When did they reach 60 billion? Thank you. Okay. So what we're going to do is go to your table, hit second graph. When you're year 0, you spent $51 billion. What was year 0? 1989. Year 1 would be 1990. Year 2 would be 91, year 3, and so on and so on. So as you're going through this, we know that year 0 was 1989 according to our data, 1990, 91, 92, 93, 94, so on, so on, so on. Where did it cross $60 billion threshold? In 1993. That's how you do that. Roughly the year 1993, people were spending $60 billion a year on long distance phone calls. Yes, sir. I'm with you on that one, and yes, you can, and I'm fine with in 1993 it happened, and I'm okay with that. And I know what you mean by that. I'm not worried about being specific, October 3rd. Okay. 93, that was a good year. I graduated high school. Yeah, you know, I was making a lot of long distance phone calls back in '93. Many quarters in the machine on that one. Yeah, started at 61. Now, the last one on here before we run out of time was the firefighter one. Are you starting to feel a little less stressy?
Yeah.
You'll get better at it. It takes time. Okay. So, firefighter. There's a house on fire. And there's a firefighter. And that firefighter has a fire hose because what they use to put out fires. Sometimes. And what I got nothing. The firefighter has this formula because you know nothing says fight fires like a math formula. So if you think about it, what is the 3 representing in this model? The head of the hose is the fireman's holding it, isn't it? Yeah, my little friend. Okay. So he's out there holding. Got her on that one. So. So, fireman, the hose basically starts here and does that, right? The window is how many feet up in the air? That's the problem. How many feet up is the window that he's got the fire out? 25 feet. So, basically that means at 25 feet, there's going to be 2 different distances he can be standing away from the window in order for it to work. Because you've got your horizontal distance that you can be standing. See where I'm going with that?
Yeah.
Because he can be close to the fire and just shooting up, or he can be really, really lazy because it's hot. And he's got the arc, he's using the jet stream or whatever you want to call it. I don't know, I've never fought a fire. Now, there's a new button that we haven't used yet on the calculator. It's okay. It is not called trace. Trace is a horribly inaccurate way of doing really anything. It really is. I don't know. So what I'm going to do, I'm going to put in both of the formulas, the 0.003x squared plus 0.62x plus 3. And I want to see where it's going to run into your y equals that height of 25. So I'm going to put a second equation in of 25. Okay. Now, I need to adjust my window for all us to see again. So go ahead and hit your graph to see where it's at, and then you can adjust accordingly. All right. Well, that didn't help us very much, though. It looks like our x max might be okay, but we obviously need to raise up our y value, our y max, and get rid of the 0 from the y. We okay with that? So I'm going to go to a y maximum of maybe 40 and put 0 for my y min. And just see what happens. I'm close enough. Do I really need to know how far out the actual hose shot? No, because I'm looking to figure out where these 2 intersection points are. I need to figure out where does the graph wind up equaling 25. Well, you can do one of 2 things. If it winds up being a clean-ish number, you can go through your table. And you're looking for where those 2 numbers are equal. And it's not, you can scroll through all of it. Or, second, calculate. I want to figure out where 2 lines intersect. I don't know. Maybe the one that says intersect. Now it's going to ask you some questions. Okay, it's going to ask you some questions. First curve. So I want to figure out the intersection on the point on the left first. So I'm just going to move my cursor over. The closer I get to where they intersect, a little bit more accurate it winds up being. So the first curve, I'll just leave it there. I'll hit enter. Second curve. Notice how it flips over to the red line? I'm going to hit enter again. Guess. I don't care. There's your intersection. 45.5 from that spot. And then I do the exact same thing on the other. I look for the intersection over there. So I have to redo all of that. Second, calculate, intersect. First curve. Well, yep, I'm on the first curve. I just got to rotate around to the other side. It's good times. Yours is much easier than mine. Almost there. Almost there. Is that what it was? Jeez. 161 and change. So the fire ring can be either 45.5 feet away from the fire, but if that's too hot, he can be 161.16 feet away from the fire. It doesn't burn his toes. Yes, ma'am. That's fine. And then you just work through it backwards that way and get your zeros. That works the same way. That's a perfectly fine way of doing it. I think that doing it this way, by understanding what is it you're looking for, you're trying to figure out where does it equal 25, and where your number is close-ish. Okay, yeah. And you're doing the exact same thing. I'm looking to see where do they equal. By you doing it, setting it equal to it, you just did it instead of just a different side. Okay. I didn't let the calculator do the work. You did a little more math than I did. I know it's okay. All right. So let's do this. On the third page, here, you should be able to do all on page 3 of these, all 4. There's only 1, 2, 3, 4. They're real quick. It's all calculated. And then on the back page, the last page, so page 3, and then page 4. I want you to do quadrant 1, quadrant 3, and quadrant 4. Oh. I cut your workload down. Just do quadrant 1 and quadrant 3. Yeah. Draw a picture of somebody putting out a fire that's 161 feet away. And then just write not to scale and you'll be fine. We will work on what's called the initial velocity tomorrow. And if any of you guys, are you guys in physics this year? You guys have done it. Okay, then you know you kind of have the idea. Initial velocity, like when you hit something moving downward, it's moving towards the Earth at negative 16 meters per second squared. Okay. What's up? Help yourself. Sign up. Okay.